In this video we will review some new topics that were not covered in the two previous videos on the RST controller. As you can see, I have also added a QR code in the slides so that you can easily access the video course on YouTube. Well, the first topic concerns processes with an input delay. As you can see here, there is an input delay in the continuous time planned of one sampling period. So if you take the ZOH discrete equivalent, you'll have a z-1 appearing. And then if you take the numerator polynomial and the denominator polynomial, BZ and AZ, this input delay is not taken into account. Well, if you run these three first commands, indeed what you obtain here is the ZOH discrete equivalent with the z-1 that I had announced. But if you take the numerator and denominator polynomial, this is what you obtain, and as you can see, this one is not taken into account. So what we had to do is, put a 0 in front here and put a 0 at the back over here. Well, it turns out that MATLAB has a command that is called AbsorbDelay, and as the name suggests, the input delay is absorbed in the transfer function. And then if you take the numerator and denominator polynomial, this input delay is taken into account. Well, this is the result of what you obtain after this command AbsorbDelay, and as you can see, the z-1 has been integrated in the transfer function, and in such a way that if you take the numerator and denominator, you have these zeros at the front of the numerator polynomial and at the back of the denominator polynomial, that are prepared there for you automatically. So it's much easier to use this command AbsorbDelay than to manually put these zeros in front and in the back of these polynomials b, z, and az. We can illustrate this using exercise 1 of the previous video. In this exercise, this is the plant that you had, the process. You can see that there is an input delay over here, and if you take the ZOH discrete equivalent, there will be a z-1 appearing, and this is why we had to add the 0 in front over here and add a 0 at the back over here. If you run this code, indeed you see this z-1, and we can check that this is indeed correct. This is the 0 that we have added at the front, and az is correct as well. This is the 0 that we had added at the back of this denominator polynomial. Of course, instead of adding those zeros manually, it's much easier to replace this line over here by these two lines. So you integrate the delay in the transfer function using the command AbsorbDelay, and then you can simply take the numerator and denominator. This is what you obtain when you run the code. As you can see, the z-1 has been integrated in the transfer function, and then you can simply take the numerator and denominator polynomials, and of course you obtain the same result. My advice to you would be to use this command AbsorbDelay. This will make things easier, especially if you want to write MATLAB code to design an RST controller automatically for any process. This is not that difficult. It is not covered in the course, but I'll leave it as a challenge to you. In the next topic, we'll deal with load disturbances, output disturbances, and sensitivity to noise. Load disturbances had been tackled in the two previous videos about the RST controller, but we'll also deal now with output disturbances and, very important, sensitivity to noise. Well, we had seen previously that the A0 polynomial, the observer polynomial, which models the parasitic modes, actually disappears from the closed loop transfer function from set point to controlled output. And you can see this over here, right? This is this ratio that you find over here, and you can see that the A0 polynomial cancels out, right? We had seen also that, well, you should select the roots or zeros of this A0 polynomial, of course strictly inside the unit circle, but it's a good idea to select them in the region of good performance that we have introduced previously. In the course, I had most often chosen the roots of A0 at the origin. Okay, but we had also seen that this might not be a good idea, because you can use the roots of A0. They do not have an impact on the closed loop transfer function from set point to output, but to influence the load disturbance. What I will show next is that you can also select these roots to influence the output disturbance and the sensitivity to noise. So really here there is a compromise. The roots should be chosen to have the correct balance between load disturbance, output disturbance, and sensitivity to noise. Well, we had seen that this A0 observer polynomial does not disappear in the transfer function from load disturbance to output. So by playing with the roots of A0, you can actually influence the load disturbance. What I've now added in the course is 2 slides. One slide talking about output disturbances and one slide, well, talking about the sensitivity to noise. As you can see, the A0 polynomial also appears in the closed loop transfer function from output disturbance to output. So by playing with the roots of A0, you can also influence the output disturbance rejection, right? But of course you'll have a compromise, because if you change the roots of A0, you're influencing load disturbance, output disturbance, and you will see in the next slide that will also influence the sensitivity to noise. So choosing the roots of A0 is really balancing between those different objectives. As you can see, the A0 polynomial also enters in the transfer function from noise to output. Right, so you can use the zeros or roots of A0 to influence the sensitivity to noise. And since we're talking about sensitivity, well, it's probably a good idea to look at the body diagram of this transfer function and to play with the roots of A0 in such a way to reduce the peak sensitivity and the sensitivity to noise in the frequency ranges where the noise content is high. And this will be illustrated on the tutorial example next. Well, we've seen previously that the transfer function from noise input and the noise affecting the output on the process to actual controlled output, and this time I'll write it as PV, process value, is minus PC over 1 plus PC. So this is minus the complementary sensitivity function, and this complementary sensitivity function is shown over here. And indeed this corresponds because, well, you can play with the sensitivity to noise by pushing the complementary sensitivity down in these frequency ranges here, and also you might try to limit this peak. So what you can do for the RST controller is play with the roots of A0 in order to achieve this insensitivity to measurement noise in the, well, high frequency ranges. This is where the noise is present. Well, remember that the RST controller is a 2-degree of freedom, so this transfer function from noise and Y in this case will not correspond to minus the transfer function from set point to controlled output, right? But we can still have a look at the body diagram of this transfer function where A0 plays a role. What you see here is the example that we've treated in the course, the so-called tutorial example, and you see here the application to noise sensitivity. You can see here the Bode diagram of the transfer function from noise to controlled output, and as you can see or remember, well, this transfer function is indeed influenced by the observer polynomial AZ. Well, what you see here in blue is the noise sensitivity when all the roots of A0 are at the origin, and here you see, well, the noise sensitivity when we change the location of the roots. And as you can see, indeed you can use these root locations of the observer polynomial to influence the noise sensitivity in the high frequency range. So if you work on a practical example where of course the controlled output will be subjected to noise, you'll have to play with the roots of the observer polynomial to improve the noise sensitivity. The next topic in this video concerns performance according to the ITAE criterion, and as you can see, well, these slides are for your information only. Well, in this course, in order to impose performance, we have worked with the following second order system, right? And the idea is that you can link the specifications in terms of rise time, settling time to an overshoot to zeta omega n, right? And then you impose the closed loop transfer function. If you need a closed loop transfer function that is of higher order than n is equal to 2, what you do is to associate this transfer function with sufficiently fast poles so that the resulting higher order closed loop system does not deviate too much from this second order system. Well, another strategy is to select the nth order closed loop transfer function according to the ITAE criterion, and I'll come back to this criterion later. Well, using this criterion, it's possible to come up with closed loop transfer function that take this form over here, where n here is the order of the transfer function. So I've shown here the transfer functions from n is equal to 1 to n is equal to 6. So they have been pre-computed using optimization, right? So if you have a transfer function of order 5, what you should do is select this transfer function over here, where you put this polynomial here at the denominator of this transfer function, and then the only thing that you have to do is to select omega n. Okay, what is very important is that if, for instance, you have n is equal to 5, the link that we had between omega n and rise time, for example, is no longer valid, because this was valid for this second order system. Notice also that, well, this transfer function for n is equal to 2 corresponds to this second order system, where zeta is this coefficient here divided by 2. Well, for your information, this is how the step responses associated to these, well, 6 transfer functions look like. As you can see, well, the overshoot is limited. There is no way to influence the overshoot. There is only one parameter you can play with, and it's omega n here. For the 6 transfer functions, we have set omega n is equal to 1. So in this type of, well, choice of closed loop transfer function, the only parameter that you can play with is omega n to influence, for instance, the settling time. So that you would know what the ITAE criterion is, it means integrated time absolute error. Well, this criterion is linked to this integral. Remember that E, that's the control error, is set point minus PV. And in this integral, well, you look at the absolute error of this quantity here, the control error, right? And you multiply it by t. So that's the time that starts to run after a set point change, right? And if you compute this quantity, you obtain the so-called ITAE criterion. So what has been done in the slide that I've shown previously is that you fix n, so you fix the order of the transfer function, and you look for the transfer function that minimizes this criterion over here, right? And what you obtain is, well, the table that I've shown in the previous slide. Well, let us go back to the first exercise that we have tackled in the second video on the RST controller. Here is the process, here are the specifications. I won't go over all the details, but remember here that we needed a closed loop transfer function, a desired closed loop transfer function of fourth order. So what we had done is to take this strategy where you imposed a closed loop transfer function that mimicked a second order system, right? That was influenced by zeta and omega n. Of course, here we have to impose the discrete version of this, and this is discussed previously in the course. And what we had done is to associate two fast poles, and here they are poles at the origin, right? And if you look at the selected step response that corresponded to this closed loop transfer function, this indeed corresponds to a zeta of 0.5 and a closed loop time constant of 4 seconds. So what we can try to do now is to impose performance according to this ITAE criterion. And remember that in the ITAE criterion there is just one parameter, which is omega n, right? So we only will ask for a closed loop time constant of 4 seconds. The damping, the overshoot, is kind of imposed by the closed loop transfer function itself, as there is only one parameter. So what we'll do here, and remember that we want a closed loop transfer function of fourth order, is look in the table that I've shown previously, select n is equal to 4, and impose the denominator polynomial as follows. Remember that this is the denominator polynomial in continuous time. So what we'll have to do is compute the roots in continuous time, transform them in roots in discrete time, and we know that this is using this relation here, and then construct the discrete denominator polynomial. And here we'll take the real part of this because the complex conjugate poles might not cancel out perfectly, right? And the only thing that you have to play with a little bit is this omega n, right? Because for an n is equal to 4, we do not actually know the relation between the performance specification on the closed loop time constant and its link with omega n. So you'll have to play a little bit with that. This is the closed loop step response that you obtain using this closed loop reference model using the ITAE criterion. As you can see, the overshoot of course is much smaller, but this corresponds to roughly a closed loop time constant of 4 seconds, which corresponds to a settling time of 20 seconds. So this is something you might want to experiment with in your control lab in order to bring some originality. The next topic concerns the correct implementation of the RST controller in the presence of manual mode, limitations, and feedforward. As you can see, this topic has given rise to a new subsection that you can find in the table of content. Well, a first naive but incorrect implementation would be to do the things as follows, right? And this is simply an incorrect implementation, because if the RST controller has integral action, so, well, one of the roots, at least one of the roots of RZ is 1, well, this will lead to integral windup. This is because, well, the output that is generated by the control law is no longer applied in the case of a manual mode or in the case of output saturation. For instance, in the control lab, the output can be saturated because the, well, heating power is limited in between 0 and 100%, right? So what is being computed is not applied on the system, and this can therefore lead to integral windup. This is something that we had encountered also for the PI controller. Well, in order to come up with a solution, observe the following equivalent implementation. So what I'll do, I'll call this input in, I'll call this one out, and we have here also in and out, and you can very easily see that these are equivalent implementations. So if you look at this, out is equal to in, not plus, minus RZ minus 1 out, right? So this is in minus RZ out plus out. These two cancel out. You take this one on the other side and you have out is equal to in over RZ, right? And this is precisely what is implemented over here. So as you can see, these are two equivalent implementations. Note that RZ minus 1, right? Because RZ takes this form over here, it's a monic polynomial. Well, RZ minus 1 can be written as follows, and this can be, well, interesting for the Simulink implementation. So let us take this equivalent implementation that we had found and add feedforward. Well, the idea will be to put the manual mode and the limitation in here, right? But if you put the limitation here, you'll have a problem because, well, at the end you will add the feedforward and you want the sum of the control action plus the feedforward, well, to be limited. So what we'll do is, well, put the feedforward here at the front. But if you put it at the front, of course, you change the implementation, because if you add it in the front, well, you should not have the feedforward. You have added too much in this loop here that comes back, because the feedforward is only added at the end. So what we'll do is add it in front and we'll subtract it in this feedback path, and again you obtain an equivalent implementation. So what we have done here is take the previous implementation, right, and we have added saturation, right, and we have added the manual mode. Remember that the manual mode is that when this Boolean input is set to 1, well, this input is selected and this input comes from the operator. So in manual mode, the operator is actually imposing the controller output. And with this implementation, you will not have integral windup. So this is how you should implement the RST controller with feedforward, manual mode, and limitations, right? So here maybe I should put a logo that this is very important, right? So in your Simulink implementation of the RST controller, you should, well, remember that you should use this correct implementation. There is something similar going on for the deadbeat controller. So if you implement a deadbeat controller with manual mode and saturation, you should do something similar, but I will leave this as a challenge to you. Notice that the reason why this implementation will not lead to integral wind-up in the presence of manual mode and saturation is because what is actually implemented or applied to the process is also what returns to the controller in this feedback bond. So it's impossible to have integral wind-up.